Hello, everyone. Welcome to this recitation on AEs and VAEs. As usual, and let's get started. The autoencoders are a type of neural networks that consists of an encoder and a decoder. The encoder takes some input data and learns to generate a lower dimensional representation of the input data. And this representation is by convention called the latent representation. And also a decoded portion of the model, which takes the latent representation and tries to generate an output that matches the input as close as possible. And another important point about this architecture is that training it does not require any labels. You just need some input, and the model will automatically learn some important information about it, represented as the latent representation, and learns how to generate an output that only needs to match input, so you do not have to provide any label to it, which is very good news. And here's a simple example of AE. So taking the MNIST dataset, which are 2D inputs of grayscale, you wanna well, one of the tasks is to classify which digit is it about. And in this case, AE will instead try to learn a representation, a latent representation by its encoder, and generate an output that matches the input by its decoder. And yeah, so comparing the previous slide, this is the encoder, this is the decoder, this is the latent representation, lower dimensional representation, and the input output. Right. And there are many implementations for architectures of autoencoders. And for MNIST, I think using some simple linear or convolution layers is enough. For more sophisticated tasks, you might consider more complex architectures, maybe some deep recurrent convolutional networks, something like what you implemented in HW part 2, just that it is trained by different loss functions. And also in most cases, or in some cases, the decoder is just a mirror of encoder, which means that you just reverse your step of generating a hidden representation, which makes pretty much of sense, right? Yeah. And since the training objective is to minimize the difference between inputs and outputs, there are some famous loss functions that we can use already. One of them are MSE losses, which take an input and output vector. For each entry in those vectors, you calculate the square of their difference and take a mean of them. Or L1 loss, which is basically MSE loss. Instead of calculating the square error, you calculate the absolute value between between the input and outputs and just take a sum. Or the binary cross entropy loss if the input and output are 0, 1 vectors, meaning that for each entry in the input or the output, they are either 0 or 1. And this is just a simplified version of cross entropy. Nothing magical here. Right. Applications. There are several applications of autoencoders. One of the most straightforward application is to generate a feature that represents important information about the input. So back to this example. This stuff hopefully contains more information about the input that is more valuable for some tasks, such as classification, then raw grayscale inputs. And another example will be your HW part 2, where you generate features from human faces that are used for classification and verification. The stuff you generated, the vector after your model's pooling layer can be also interpreted as some kind of hidden representation, and like what we do in AEs here, right? And another application is called data denoising. And well, if you want to train an autoencoder for data denoising, there is something that have to be changed in the training process. So in the conventional AE, you train your model to predict outputs that matches your input as close as possible. This doesn't help with denoise, right? If you want to denoise something, you want to feed it a noisy input and let it generate a denoise output, which means that instead of letting your model generate output that matches input as close as possible during the training process, you want to feed it noisy inputs. generate hidden representation and let it generate output that matches the denoised version of the input as close as possible. Right? You want your model to mimic the behavior you wanted to do during test time. So by doing this, hopefully for a given set of data, your model can learn some, characteristic of the data and how noise is added and how to remove them with the decoder. And when you actually, during test time, you feed it with noisy data, it can generate a denoised data that can be used for downstream tasks. And another kind of application is called anomaly detection, which basically means that if your model predicts output that is very close to your input and you feed it really weird stuff, then it may not work as well as the stuff that is not weird, and you can just figure it out by calculating the losses here. Yeah, nothing magical. All right, let's see an example walkthrough of a really, really simple example of autoencoder. So this is the autoencoder class. The encoder consists of a set of sequential layers where you have a 2D convolution layer, which generates more channels and shrinked vectors at each level, then a ReLU activation repeated 3 times. And so this layer generates a hidden representation, which also called the latent representation. And the decoder is basically a reflection of the encoder layer. Right. So the encoded is basically the hidden representation. And we get the MNIST datasets here. And we set the hyperparameters, the model, the optimizer, MSE loss, and we train it, right? Pretty simple approach. And then let's see how the training does. So it takes unseen data of the test loader because the model is trained on training loader, and it is supposed to generate a output that matches exactly the same as the input. So you can see it pretty much matches the input, just that it's a little bit blurry, right? These are the outputs, these are the inputs according to visualization. All right, so here's an example of image denoising. Just as I mentioned earlier, instead of training your model to ask it to produce outputs that exactly matches your input, which is the criterion we use to train this vanilla autoencoder, you want to feed it a noisy input. Well, where in this case, you just add Gaussian noise, and the output it's supposed to match your input data without noise, right? So in this way, your model behaves exactly the same as you want it to in the test time. And you train this several epochs. This takes plenty of time, so I'm not training it right now. And the output it generates is also pretty successful. See it, you add noise to the input, same input here, and your model is pretty much able to generate the denoise input. And if you have some downstream tasks, such as classification, then using these denoise inputs to classify the digit is definitely much easier to use these noisy ones. And image generation. Here, if we already trained our model to denoise, can we feed it random noise to ask it to generate some digit out of it? And it turns out that the effect is not very good, right? You cannot see what this is. This makes no sense. Just a less noisy noise. However, an interesting point here is that if you make your latent variable having the same size of your input, and you apply many layers of these denoising steps, then what you get is something like a diffusion model, and which hopefully will be covered later in the class. And we will not expand on this here, but just the conclusion is no, image generation is very bad here because this does not make sense, right? It is some randomly generated noise, not an input added with noise, and your model is not trained to do this kind of task.
Everyone, as we have seen in the previous slides, an autoencoder is a neural network architecture used to learn a representation of the training data. It is designed to encode input data into a compact form and then reconstruct the input from this representation as accurately as possible. However, this representation has some limitations due to the absence of constraint on the latent space, which is only learned by minimizing the reconstruction loss. The first limitation is the lack of control over the latent space representation. Autoencoders are not designed to control or interpret the latent space directly. This means that we cannot easily manipulate the encoded data to change specific characteristics in the output. The second limitation is overfitting. Autoencoders can easily overfit the training data, especially when the dimensionality is high. Hence, the latent representation becomes useless. The third limitation is the inability to generate new samples. By generation, I mean to create new samples that could plausibly come from the same distribution as the training data, which is beyond the capabilities of basic autoencoder. This is because the latent space doesn't usually have the capacity to interpolate between samples or create new samples that come from the data distribution. These drawbacks highlight the need for more sophisticated models that add some constraints on the learned representation. One of these models is variational autoencoders. VAEs offer a sophisticated upgrade to the traditional autoencoder model by introducing a probabilistic twist that allows them to approximate the underlying data distribution of the input to enable the model to generate new data samples that are similar to the input data distribution. VAEs provide a structured and continuous latent space by encoding input data as distributions rather than fixed points in the latent space. So the aim of VAEs is to learn the data distribution of the input data. This addresses the lack of control in autoencoders by allowing us to manipulate the latent space and mitigate the overfitting problem through a regularization effect in the variational approach, and empowers the model with the ability to generate new and diverse samples. So as we have seen previously, autoencoder learning objective was to minimize the reconstruction loss and to make the output as similar to the input as possible. But VAEs doesn't learn the latent factor directly. Instead, it learns the mean and variance of the training data. And then it samples the latent factor from this learned mean and variance. But the sampling process is not differentiable. So instead of sampling Z from the learned mean and variance, we usually sample some variable epsilon from some standard distribution, like the normal distribution, and then scale the epsilon by the learned variance and shift it by the learned mean. This means this process is called reparameterization trick, and we will discuss it later in more detail. This key difference gives the VAE an advantage. The latent space now is regularized to follow a predefined distribution, like the normal distribution, which we know its properties very well. So the objective of VAE is to maximize the evidence lower bound, but since it is intractable to compute the true posterior distribution of Z given the input X directly, we learn some distribution Q parameterized by theta, and we try to minimize the distance between this learned distribution and some standard distribution like the normal distribution that we know its properties. This is achieved by this first term, KL divergence. In the first term, we compute the distance between the learned distribution and usually the normal distribution. This encourages the encoder to learn a latent space that maintains the properties of a standard normal distribution like normal distribution, which is essential for the generative capabilities of VAE. The second term here is the reconstruction term to ensure that the model doesn't lose critical information during the encoding-decoding process. We are essentially striking a balance between having a well-structured regularized latent space from the first term and being able to accurately reconstruct the input from the second term. This balance is key to VAE's ability to not just compress data, but also to generate new data points. In summary, VAEs are probabilistic models to learn data distribution. It maps the input to a probability distribution. The objective of VAE is to maximize the evidence lower bound, which is equivalent to minimizing the KL divergence. It allows learning of a structured and continuous latent space representation.
Hello, everyone. Welcome to the last part of this recitation on autoencoders and variational autoencoders. Now that we've spoken about autoencoders and given you an introduction of the variational autoencoders, let's talk about the use cases of them. Here you can see that you have a picture of a cat, which is fed into an encoder network, and then which essentially we all know is again converted into a latent vector, and then is passed to a decoder, and then it can be used to recreate that image. One of the reparameterization tricks that we can use here is that we can convert that sample latent vector, create that sample latent vector using the mean and standard deviation so that it becomes easier to compute. So the issue is that the autoencoders was that the latent space is unstructured and difficult to interpret. The solution would be to map it to a normal distribution, and this can be done by first, as we saw in the previous slide, by normalizing it to have a standard mean and a standard deviation. So here, addressing the issues of autoencoders, one thing we could do is map it to a normal distribution so that it becomes easier to interpret the latent space. To avoid the overfitting, also normal distribution would help in restricting the freedom. Finally, giving a normalized sample vector to the decoder helps in the data generation and can be used in generating this image as shown in this picture. Now let's go through a walkthrough about how this works. Yeah, in this notebook, here we use a setup that is found in most VAE papers, a multivariate normal distribution for the conditional distribution of the latent vectors given an input image. And also we use a Bernoulli distribution for the images given the latent vector. Using this Bernoulli distribution, the reconstruction loss reduces to the binary cross entropy, and a paper has been linked here for more information. Here you can see we install our modules, and then after that, we set up our parameters. Here I've just used number of epochs of 100 and a batch size of 128 and a learning rate of 1e minus 3. So we will be using the MNIST dataset. MNIST images show digits from 0 to 9 in 28 by 28 grayscale images. And we'll be using a binary cross entropy loss that treats pixel values in 0 and 1. And we will be creating both a training and a test set as shown here. And then for the variational autoencoder, we'll use a convolutional encoder and decoder with a fully connected version, which gives better than fully connected versions. In convolution layers, we increase the channels as we approach this bottleneck, but note that the number of features still decreases since the channels increase by the factor of 2, but the spatial size decreases by a factor of 4, as you can see in these convolutional layers. And kernel size 4 is used to avoid the biasing problems, and there has been a link provided here for that. And then we use the KL divergence to find out between the pi distribution of the latent vectors. Then this is how we compute the VAE loss, and as I said, it's reduced to binary cross entropy loss. Here we train the variational autoencoder for 100 epochs. And as you can see, the loss has been going down consistently. You could also load it from a pre-trained variational autoencoder as they've provided here. And then we evaluate it on the test set. In order to visualize some of the reconstructions of what the use cases can be for using these variational autoencoders, we have given you a piece of code wherein you can look at how the images have been reconstructed. Here are the original images, and these are the reconstructed images. And interpolating in the latent space can also be done by looking at how these images have been created with various lambda values, and that has been shown here. And this has been achieved. This has been possible because of the normalization we did, and we can interpret the latent space much better. And sampling, there is another method of doing sampling the latent vector from a pair. A variational autoencoder can draw latent vectors from the pair distribution and generate new digits. Although the generated digits are not perfect, they're usually better than a non-variational autoencoder. Similar to autoencoders, the latent vectors is parser in higher dimensional latent spaces. Increasing the weight of the KL divergence makes it less sparse and makes it less sparse, but also gives you a lower quality reconstruction. And this is a trade-off that is to be considered. Here you can see that we sample the latent vectors and then reconstruct them. And then this is the 2D space that has been there for MNIST. So we hope that this notebook helps you in understanding how to reconstruct images using variational autoencoders. And not just that, it can be used to generate images. And we hope that the latent vector space representation can lead to certain other research can lead to certain other ideas that can be used in other research problems. Thank you.